Okay, welcome to the lab here. Get started here in just a sec. And like I said, I think we're just going to kind of finish up. We don't have that much more to go. Just talk about a few more things and just kind of finish it up here. What we were talking about in lecture. Okay, so we've been talking about here sort of the effect of temperature on the rate. And as we talked about, the rate, again, typically will increase as we increase the temperature, again, because we're adding all that extra energy. That's going to allow a greater proportion of molecules to get up and over that activation energy and really get to the other side. And obviously, as we talked about as well, vice versa of that, if we sort of lower the temperature, we're removing a lot of that energy, and we're going to have a smaller proportion of molecules that have enough energy really to get to the other side. So why don't we start off here with this next example here, take a minute or two and calculate it. Again, we often say that the reaction rate doubles for every 10 degrees Celsius change in temperature. Calculate the activation energy here. Again, here you could use as a hint there, you could use 300 Kelvin for temperature 1, 310 for temperature 2, and the relationship there of the rate doubling. So take a couple of minutes and see what you come up with. Okay, so let's take a look at this here and see. Let's flip the page here. I get something to write on. So obviously we're going to use our equation that we saw earlier, where sort of the non-graphical approach there. So in this case, they didn't actually give us the actual values of K1 and K2. But they did tell us that when we do increase the temperature, which we're going to call T2 310 and T1 300, that we do see that the rate will double. So it basically doubles from K1 to K2. So that means, as we saw there, that the K2 equals basically 2 times the value of K1. So ultimately what that does is when we put it into here, we get 2K1, which is double the first rate constant. Those guys cancel, and we essentially end up with a natural log of 2 on that side, which basically means that it doubles. Our E of A is 8.314 joules per Kelvin per mole. 1 over our temperature that they chose, which was 300 Kelvin, minus 1 over our 310 Kelvin in that particular case. And again, you could have technically chose any sort of 10 degrees Celsius difference in terms of the temperature around sort of roomish temperature, if you will, would come out about the same. Natural log of 2 times 8.314 going to give us something like 5.7628 equals E of A. And if we clean up what's in the parentheses there, 1 divided by 300 minus 1 divided by 310 gives us something like 0.00010757. We're going to divide that to the other side. So if we do that, going to give us an E of A of 53594. Again, these are going to be joules based off of the gas constant. And if we convert that into kilojoules, which is typically what our activation energy is, we end up with something like 53.6 kilojoules per mole. And again, if you chose 2 different temperatures, but you kept it around the same sort of temperature range, you won't get the exact same number every time, but it'll be pretty close. So for example, if you went up the next 10 degrees or something, it might be 54 or 56, but in that sort of general ballpark. Question on how to use our Arrhenius equation here. Okay, so I just want to finish talking about a couple other things. You're not going to have to worry too much about sort of what we're going to talk about here in terms of reaction mechanisms, but I do just want to kind of cover it just so you've seen it, and that way maybe if it comes up again on your final in 200B, you'll be okay. I got this number here, which I think is your question, by taking the natural log of 2 and times it by 8.314. So times 8.314 get you there. Yeah. So again, we're going to talk a little bit about reaction mechanisms next. And again, you don't have to worry about it in terms of the final or anything like that. It's just, I feel like you should probably just see a little bit of it so you've been exposed to it, just in case. So what we're going to talk about here is, again, this diagram here is sort of what we were talking about there. Again, just to reiterate that even though, 2 things do sort of collide together, it doesn't necessarily mean that it will always result in sort of products being formed. They do have to sort of hit each other, like we talked about, with the right amount of energy and sort of the right orientation. And as you can see here, sort of the orange and purple come together. That's good. That's going to promote products being formed here. But if this collision occurs in sort of the opposite way, sort of the CH3 part back here where the carbon is and the potassium, you're not going to get any products formed. So Again, this just illustrates that idea as we talked about that not 100% of the time when something collides will you actually produce products. Those two sort of important things that we've been talking about does has to take place. They do need to hit each other sort of in the right location, like in this case, the purple and the orange versus sort of the orange and the black sort of circles. And then also obviously hit each other with the correct amount of energy, you know, to sort of start the process of breaking bonds and making new bonds when they do hit. Now, another important thing in terms of sort of reactions and how they take place is this idea of what is referred to as reaction mechanisms. Now, a lot of times when we think about reactions, we sort of think about them as sort of a one-step process, like we go from reactants to products. Like if we take this particular reaction here, we oftentimes would look at it and just go, okay, it just directly goes from here down to here. And for a lot of reactions, that's really not the case. So a lot of reactions actually occurs in several different sort of steps along the way. And you basically can add up all these steps and get the overall reaction that's taking place. So a number of reactions really don't proceed as we sort of perceive it as a one step here to there type of situation. It may involve many steps, many individual reactions when sort of taken as a whole gives you that overall reaction that we typically focus on. And these sort of individual steps are sometimes referred to as elementary steps in a reaction mechanism. And really what a reaction mechanism is sort of a plausible way for a reaction to take place. So it's a possibility of these are maybe the steps that occur that leads us to products being formed. We'll talk a little bit and just in general, if there is perhaps a mechanism that is sort of proven to be a sort of good mechanism, it doesn't necessarily mean that 100% of the time that's always sort of the route or process at which that reaction takes place. It just means that these are a possible, probable way that that reaction could occur through these series of steps. The reason why we think about these things not occurring as sort of a one-step process going from reactants to products is, for example, if we do take that reaction that we're looking at here in the middle of the screen, when we take NO plus O2 to form NO2, which is a bad brown gas that happens, during that process, we actually see the formation of N2O2. So that dinitrogen dioxide there is formed in the process of this and is detected. But when we look at the overall reaction there, we see no N2O2 present anywhere in this overall reaction. So this is the overall reaction of the formation of NO2. And nowhere in this overall reaction do we see this guy there. But when this reaction actually does take place, you could test for it and you can detect it actually being formed. So what this implies is, unlike where the reaction looks like, it doesn't necessarily occur all in one step. There must be a step somewhere along the way where this N2O2 was made. And there also must be a step along the way where the N2O2 gets used up. And that's why it does not appear in the overall reaction. So sort of a proposed mechanism for this reaction to occur is a two-step process where we see at the bottom here. And in this two-step process, what we are able to see is the possibility that what maybe occurs first is two of these NO products actually come together to make that N2O2, which would account for why it's detected when this reaction takes place. And then in sort of a second step in this mechanism, that N2O2 gets completely used up to make the NO2 gas, which is really the product that wants to be made here in this reaction. So we could add together these elementary steps and cross out whatever is the same on opposite sides of the arrow. So in this case, the N2O2 will get crossed out. And that will leave us our overall reaction here. And this would explain and account for the reason that we do detect this N2O2 in this reaction, although we do not see it actually present in the overall reaction. When we produce something like this that gets produced early on in a sort of mechanism, but gets used up completely when it's all said and done, as we'll see, that is what is sometimes referred to as an intermediate. So an intermediate is some type of substance that gets produced early on in sort of a reaction, gets sort of completely used up, is not present at the end of the reaction. And again, that's what's sort of the definition there of our intermediate. And that's what we sort of see here in this sort of mechanism process here. Again, we get this formation of this intermediate. It then is sort of used up in the secondary step and is not left over when it's all said and done. Gets completely used up as the process goes on. And that is your basic definition of an intermediate. And an intermediate should not be confused with something else that may appear to be an intermediate. So what I mean by that is there could be times when you add up individual elementary steps along the way and something cancels but doesn't completely cancel out, so it sort of reduces down. So this is very similar to like when we did redox, where you had waters on each side, you kind of cancel out everything that's on opposite sides of the arrow. Now there could be a case where you cancel something but it's still there and it does appear in the overall reaction. That would not be considered an intermediate. So an intermediate has to be sort of formed early on in a step and then get completely used up by the time it's all said and done. An intermediate should not find itself in the overall reaction. And again, in this case here, the N2O2 not in the overall reaction, so again considered an intermediate. When we talk about these sort of elementary steps, we can sort of describe them in terms of how many molecules basically sort of react. In a elementary step where there's only one molecule reacting, that is sometimes referred to as unimolecular. When we have an elementary step where there's two molecules reacting, that's sometimes referred to as being bimolecular. And elementary step when we have three of them sort of reacting, that is termolecular. And really, if you sort of think about a lot of reactions that you come across and so forth, you know, we oftentimes only have a lot of times one reactant, two reactant, maybe three reactants. You know, we don't really technically have like, you know, a lot of times reactions where there's like 4, 5, 6, 7, 8, 9, however many reactants all reacting at the same time. And we typically don't have reactions like that. And that's why when we talked about those orders earlier, when we talked about first order, second order, and zero order, those are typically the orders that would encompass pretty much all the types of reactions that you would probably come across. Again, think about something that has only one reactant. It probably could be maybe a first order, second order, or zero order. Maybe two reactants, each first order gives you a second order overall, or one first order, one zero order gives you first order. You know, we typically won't get above first, second, or zero in terms of the orders because of this sort of situation here. We typically don't have that many reactants reacting at once. So in terms of sort of overall orders or reactions, you know, we sort of top out at, you know, kind of first, second, zero order. You know, very rare can you, in a real life sort of situation, get, you know, third, fourth, you know, type of orders. In theory, they're possible, kinetic wise, and sort of ability to truly probably happen, maybe will not happen so much. So we can classify this. So when we look at these elementary steps here, these two elementary steps, they are both bimolecular, which means that they have two molecules each basically reacting. Now, one thing that's very different when you're talking about mechanisms than when you're not talking about mechanisms, and in terms of the rate law, is if you remember what we talked about at the beginning of this chapter, it is true that the rate law and the orders, for example, are found experimentally. And the one sort of exception where you can ignore that and use the actual balanced equation to write a rate law is for when you're doing elementary steps. So when you're doing these elementary steps, you can actually use the coefficients as the orders, and that is the only place you could do that. So pretty much for our class, you should not do that unless you're specifically doing mechanisms. And since you won't really be doing mechanisms, you don't have to worry about it. But you can write basically a rate law here for each of the elementary steps using the coefficients as the exponents. So for example here, this would be rate equals k to the a to the 1. This would be a to the 1 and b to the 1. Here the coefficient technically is 2a, and that's where the 2 comes from here. So again, like we talked about at the beginning of this chapter, you should experimentally find those everywhere else other than doing mechanisms. So again, this is specifically the only place where that is acceptable to do. Otherwise, you should use the information, the tables like we did in this chapter earlier to calculate the actual orders. Now, in order for a mechanism to be really a good mechanism, or really what is sometimes referred to as a plausible mechanism, which means, again, this is a possible way this reaction could occur. There's really two main things that has to happen for it to be sort of a good mechanism. First off is pretty simple. If you add up all the individual steps and you cancel out everything on opposite sides to cancel, what you should be left with is the overall reaction for what you're looking for. The second thing that has to happen is the rate determining step, which is sometimes referred to as the RDS, is what is referred to as basically the slowest step in the mechanism. And it is the slowest step in the mechanism. It is the one that basically will determine how fast that reaction will take place. You know, there may be 2 steps, 3 steps, 4 steps, but somewhere along the way, there's this slow step. And this slow step is pretty much what everybody is waiting for to sort of take place in order for that reaction to sort of complete. And it really has the biggest effect on the overall rate of that reaction. It's like when you're at the supermarket and the 10 items or less, and somebody's got like 500 items, that is your rate determining step. You have to wait for them to get through before you could get through. Obviously, even though you have like 2 items, it's going to take as long as that guy takes to basically get through the line. And that's basically what the rate determining step, it is basically the slowest step in the mechanism. And the rate law that you could write for the slowest step in the mechanism should match the rate law that's been found experimentally. So in mechanism problems, there's a few different types of mechanism problems, and I don't think we're going to go into great detail on those, but in certain cases, they will actually tell you in the problem, hey, the observed rate law for this reaction was this. And what that means is when you figure out the rate law for the mechanism, for the slow step, it should match the one that was found experimentally. If it doesn't match the one that's found experimentally, then it is a bad mechanism. If it does match, it's a good mechanism. The other way that you can figure it out is the actual steps in the mechanism will be labeled. They'll say, this step is fast, this step is slow. And that's a pretty easy way to figure it out. The one that's labeled slow is the rate determining step. So that's, again, a very common way that you can sort of determine, you know, which one is your rate determining step. All right, so let's take a look at one type of mechanism problem here, just to kind of give you a feel for, you know, what they sort of are. So for example here, this experimental rate law for this reaction is that the rate is the rate is equal to K times NO₂ squared. The reaction is believed to occur through these 2 steps. What is the overall reaction? What are the intermediates? And what can you say about the rates? So again here, what we can do with this is we could take both of these steps and we could add them together. And if we take both of these steps and add them together, we want to cancel out whatever's on opposite sides of the arrow that are the same. So NO3 here will cancel. NO2 will cancel. And what that leaves us is whatever's on the left-hand side stays on the left-hand side. Whatever's on the right-hand side of the arrow stays there. That gives us NO2 plus CO gives us NO plus CO2. So this would be our overall reaction based on this proposed mechanism. Now this type of mechanism problem, we can't really determine if it's good or bad, this mechanism. because they didn't give us the overall reaction, so we can't really compare to make sure it's the right one. But this would be based off of this mechanism, the overall reaction that we're looking at. And it does sort of match what it says, the reaction between NO2 and CO to produce NO and CO2. So, you know, that's pretty good in terms of matching what they basically say the reaction is going to be. Now, in terms of the intermediate here is the NO3. Now, you may say to yourself, didn't we cancel out the NO2? And we did cancel out the NO2, but when we look at the NO2, we didn't completely cancel it out. And it still appears in the overall reaction. So although we did cancel out a little bit of that NO2, because it still appears in the overall reaction, it is not an intermediate. And again, a reminder that the intermediate is something that is produced early on, like the NO3. And the second part of that is it gets completely used up by the time the reaction's over. And it should not appear in the overall reaction. So when we look at this one, the NO3, does not appear here in the overall reaction, so it would be the intermediate. So if you're asking how do we add those together, if that's sort of what you're asking, we just add basically both of those reactions together. So we had this, right, plus this, and NO and NO3, and NO plus CO, NO2 and CO2. So basically when we add reactions together, 2 reactions, 3 reactions, you can do it one way. You could either just keep everything on the left, everything on the right. If you keep everything on the left over here, that's a 3, there we go. You can just write everything if you want. So you would have 2 NO2 plus NO3 plus CO goes to NO plus NO2 plus NO3 plus CO2. And then you could just cancel out things. Again, the arrow is like an equal sign. So if you subtract the NO3 from both sides, it cancels. If you subtract the NO2 there from both sides, it will also cancel one of those guys. And that will leave you the NO2 and the CO, the NO and the CO2. So you basically just add them together. Anything on opposite sides of the arrow can cancel or reduce down. And at this point, it should be balanced. We have 1 nitrogen on each side, 3 oxygens on each side, and 1 carbon on each side. That would give us the overall reaction. So when you're doing mechanisms, you'll have a bunch of steps. In this case, there's just 2 steps, could be 3 steps, 4 steps, 5 steps. You just add them together. And again, it's very similar to what we did with the redox when you sort of added the 2 half reactions together. You cancel out whatever's on opposite sides of the arrows and stuff like that. But again, here, the NO3 would actually be the only intermediate that's present because it is the only thing that gets used up completely and made. It gets made and then used up completely, does not appear in the overall reaction. Now, because this is a mechanism, and like I said before, because it's a mechanism, it is the only place where you can use the coefficients as the exponents. So I'm just going to kind of erase some of this so we can actually see these guys again. So we can write for each of these individual steps an actual rate law. So if we write for step number 1, the rate law, it would be the rate is equal to K times NO2 squared. Again, the coefficient here would be basically 2 NO2. If you add both of these together, and again, that is where the 2 comes from. And because this is a mechanism, we can do that. For step number 2, we would write that the rate equals K times NO3 times CO. So again, only in mechanisms and these elementary steps can you write rate laws for each of the individual steps. Now, if you remember, in order for a mechanism to be good, the rate determining step should have the same rate law as the one that was found experimentally. So in this particular problem, what they told us was experimentally, the rate law was found to be this right here. And if we look at the rate law for each of the steps, what we see is step number 1 here has the exact same rate law as the one that was found experimentally. So what that would tell us is because step number 1 has the exact same rate law as the one that's found experimentally, it would tell us that this step here would be our slow step, step number 1. This would be our fast step. And more importantly, our rate determining step would be step number 1. So in this particular mechanism, in this possible mechanism, the one step that really determines the overall rate of the reaction would be step number 1. It is our rate determining step because its elementary step there, step number 1, has a rate law that matches the one that was found experimentally, and that would imply that that is the slow step in the mechanism. Any questions on that? Okay. So that was just a little bit about mechanisms. And again, there's a few different types of mechanism problems, but we're really not going to really worry too much about that. So I just want to at least give you sort of a feeling of what mechanisms were and give you that idea of, you know, understanding that not all reactions really do take place in sort of a one-step approach. They may take multiple steps along the way to actually occur. And you can sort of propose possible mechanisms for the way that these reactions occur. And you could sort of prove whether or not a mechanism is a possible mechanism based on the rate determining step, which is your slow step, and sort of the rate law for that one versus the rate law that's found experimentally. All right, so we're just going to kind of skip these other mechanism type problems. And we're going to finish up talking here about a catalyst. And a catalyst is typically something that will speed up a chemical reaction. So when we add a catalyst, it's again it's not a reactant, and it's not a product, and it does not get used up. It is there a lot of times to sort of facilitate that reaction occurring a lot faster. Now, there are catalysts that are what are sometimes referred to as negative catalysts that can kind of slow down a chemical reaction or a reaction in general. But probably 9 times out of 10, even closer probably to 10 times out of 10, if somebody is talking about a catalyst, they're probably referring to it in the aspect of it speeding up a chemical reaction. And really the way a lot of catalysts can do that is they sort of provide a alternative pathway for that reaction to occur, a different sort of mechanism like we were just talking about, these different sort of steps. Without the catalyst there, it may go through a certain process in terms of those steps. With the presence of a catalyst, it may actually go through a couple different steps along the way that involves the catalyst. And that catalyst then becomes sort of the rate determining step and happens a lot faster than it would normally occur. And the idea there is with no catalyst present, for example, things got to kind of float around and try to find each other and go react. With the presence of a catalyst, what it sometimes can do is like, oh, everybody's sort of attracted to a central area. And by being attracted to the central area, it allows everybody to come in contact with each other a lot faster. And thus, the reaction will occur a lot faster. And ultimately, the way it's able to do that is usually a catalyst affects the activation energy. So in a non-catalyzed reaction, these guys have to climb this hill all the way to the top to get to the other side. While if we add a catalyst to the same reaction, what ends up happening because of this sort of alternative pathway, the activation energy hill gets a lot smaller, as you can see. So these guys only need to kind of get up here to get to the other side. Going to be able to do that obviously a lot quicker because it lowered that activation energy. Again, as the activation energy lowers, as it says here, as the E of A goes down, the rate constant, or the rate of the reaction, will increase. And that's typically what we see. Now, when we talk about catalysts, there's a couple different types of catalysts. For example, ones are what are referred to as heterogeneous catalysts. And heterogeneous catalysts are catalysts that are in different phases. So heterogeneous, like heterogeneous mixture, means we see different layers. In a heterogeneous catalyst, the catalyst and the reactants are in different phases. So for example, these are 3 processes here that occur. And again, by using a catalyst can help it occur a lot more efficiently. For example, the process where we make ammonia, where nitrogen gas and hydrogen gas come together to make NH3. This reaction is a spontaneous reaction, which means it does occur under normal conditions, but it's an extremely slow reaction. But if you add a catalyst there, like iron, for example, a piece of metal or something like that, what that will do is very efficiently increase the rate of this reaction, which means you can make, for example, ammonia a lot quicker. The same thing with the process of making nitric acid. Using something like a platinum wire will increase the rate of that reaction, allow the nitric acid to be made a lot more easily than it would be if it just had to kind of happen by itself. In our cars, we also have catalytic converters, right? And catalytic converters basically has kind of 2 parts. They have one part where there's catalysts in their metals that basically will increase the reaction of carbon monoxide from unburned hydrocarbon or gases. So instead of like polluting with carbon monoxide, it will kind of convert it into CO2 and water. And there's a second chamber usually in a catalytic converter where the process of doing that, because obviously the engine and everybody, all those gases are very high in temperature, sort of a byproduct of that sort of reaction there and heating that sort of fumes, is you make a lot of NO, which then can become NO₂, which is sort of a brown toxic gas, contributes to smog and so forth. So sort of the second part of the catalytic converter will kind of take care of that aspect of it. It will turn that we'll take that NO₂ basically and kind of turn it into nitrogen gas and oxygen gas, which are obviously gases that we find in the atmosphere and stuff like that. And again, these guys here utilize a lot of solid guys as catalysts. Again, in a lot of reactions, the catalyst is written on top of the arrow, like platinum or something like that. In addition, catalysts could be homogeneous, which means they're in the same sort of phase as the reactants. So common ones are acid-base catalysts. An acid catalyst is sometimes written H+ on top of the arrow. And these would be solutions. So again, floating around with everybody in the solution, there's some H+, OH-, which help sort of allow everybody to come together a little bit faster, but they're obviously in the same phase as each other in that particular case. So here's the production of ammonia. And again, these are our nitrogen and our hydrogen coming together. And again, this is a piece of iron, for example, and these gas molecules are sort of attracted to that solid catalyst. Now, when they get here, they sort of bind to this metal, and what that does is it actually will start to weaken these bonds. And it weakens the bond between the hydrogen and the hydrogen, the nitrogen and the nitrogen, and as you can see, they then are able to sort of separate out into hydrogen atoms, nitrogen atoms a lot easier. And as you could almost see, they could then reassemble here to make our NH3 molecules in that process. So the presence of this metal really accelerates the nitrogen gas and oxygen gas from just floating around freely. They kind of all congregate to this metal. And the secondary process of that is it actually helps weaken the bonds between hydrogen, hydrogen, nitrogen, nitrogen, which sort of promotes them coming apart so they can then reassemble as NH3. And you can see here, these are all the catalysts here, iron, sometimes aluminum oxide, potassium oxide are used. And you can also see that the catalyst here is pretty much unchanged in this particular reaction here. And it still is there at the beginning, it's still there at the end. not used up, again, not considered a reactant nor a product. Here's the process of nitric acid being made. And again, by using that sort of platinum wire, it helps catalyze this reaction. We do make really these two guys. This is nitric acid, which is sort of the goal of the process. We also make nitrous acid. And sort of the nice thing about nitrous acid is if you kind of heat it as a sort of a secondary byproduct here, you can make some more nitric acid, and you'll actually make some NO. That's beneficial in two ways, because now you're making more nitric acid, which is what you're looking for. And if you look at NO, it is actually part of the second step in the mechanism. So now you're making more of the product that you need to make more product. So it's a nice little loop that works really well in this sort of mechanism. It's almost not very wasteful of anything. You know, you could really generate a lot of nitric acid. You could also use that NO to generate more nitric acid as sort of the byproduct that's being made that can be fed back in to sort of the process. So it works really well in this sense. All right, that is it, they say. So that is it for chapter 11. Congratulations, that is it for Chem 200A in terms of material. So from this chapter, again, like I said, you're responsible for everything through the Arrhenius equation, activation energy, so no mechanisms. You don't have to worry about any of that stuff in terms of that. Any questions on that there? Okay. So let's talk about a couple of things here. We have one more lab that is left, and that is the rate law lab, and that is experiment 14. So experiment 14 is technically a formal lab as well, which is not going to be, obviously. So for experiment 14, what you need to do is get something to write with here. So for experiment 14, all you need to do is the pre-lab. That's it. So you just need to do the pre-lab, the questions in the pre-lab, and submit them by, we'll go with Thursday, since that's our last day, right? So we'll go with Thursday. So just the pre-lab on that one, no video, nothing like that. So that'll be kind of a good review a little bit as well, especially the last problem there, probably something similar to what you might see on the final. Just the pre-lab for experiment 14, and that will do it for the lab part as well. In addition, you do have some stuff that is due today, tomorrow, this week, right? So make sure those labs get in. It should be 11, I think, is due today. You should have 13 as well sometime, I think. 13 was due, I think, already. So 11 and this one, I think. So make sure that stuff gets in. In terms of the homework, you don't have to submit the homework for, I guess it would be this last chapter or anything like that. So you'll get credit for it if you take the final. But I would recommend, obviously, you do the homework problems, because obviously the kinetics part will be on the final as well. So you want to make sure that you do that. Any questions on any of that stuff? So tomorrow is our last official day there, and then we'll have our final on Thursday. So with that being said, tomorrow we'll do some reviewing probably. So if that will be helpful, we'll go through maybe some of the topics we talked about this semester, some of the main ideas of it. The final will probably be pretty comprehensive. Again, I'm not going to focus on one chapter over something else. So again, you just want to think about sort of the important times, important calculations that we sort of talked about, and think about. Honestly, I haven't decided yet. I'll let you know. I'm leaning towards we'll just take it like we normally do around lab time, maybe during lecture time in case there's any type of questions or something like that. You know, we'll use that for maybe just a last minute, I guess, question and answer, and then the final will probably be during lab time like we normally be doing it, I think. Other questions on any of that? Okay, so for the rest of the time and all that, I will be here in case you do have any questions on anything. But do take care of whatever you need to take care of. And tomorrow, like I said, we'll probably use the time to do some reviewing for the final, and maybe just, again, hit some of the highlights of all the chapters maybe, and again, the important sort of calculations and stuff from that. Any questions on any of that stuff? All right. Again, use this time wisely, start studying for the final, knock out whatever you got left in terms of the lab reports. Don't forget about the take-home quiz that you have. That is worth points, so make sure that you do upload those as well. Okay. All right, so like I said, I'll be